My presentation is dedicated to another simple mathematical model of aerodynamics of a wing in ground effect. And in this case, I consider classical large aspect ratio wing in the spirit of Ludwig Prandtl's lifting line theory. I'll tell a few words in introduction, then I'll discuss lifting lines in what I call moderate ground effect. We all know that Prandtl considered the following assumption: the chord of the wing should be much smaller than the span. But here, in the case of ground effect, we have another parameter, which is the distance from the ground. So we have to define orders of magnitude. And to have it treated as a lifting line, I have to assume that the distance of the lifting line of the wing from the ground is of the order of span and is much larger than the chord. So now the chord is much smaller than the span and much smaller than the distance. Both distance and span are of the same order. Only this asymptotics, these orders allow to bring ourselves to what Prandtl called lifting line concept in this case. Then I'll consider single lifting line, two lifting lines, that is tandem of large aspect ratio and moderate ground effect. And then I'll also consider, based on this model, a still simpler model, which can be called limiting case of extreme ground effect. We've already spoken about extreme ground effect, and we have defined the distance, that is the ratio of the distance from the ground, relative distance or relative clearance, to the chord. Now I introduce a small parameter, which is a distance from the ground divided by the span. This would be relative ground clearance based on span. And I'll try to organize a limiting process which brings us to quite interesting results. That is, the Prandtl's integro-differential equation becomes just a simple, ordinary differential equations of this equation of the second order. And the same happens if I consider a tandem. In this case, we have a system of two ordinary differential equations of the second order instead of two integro-differential equations in the Prandtl's series. And then we'll discuss something which is related to span-dominated and chord-dominated ground effects, which were already mentioned by Edwin in his introductory conference lecture. Now, definition, well known, ground effect is an increase in the lift-to-drag ratio of the wing moving close to the underlying surface. Since long, there has been manifestations of ground effect. I'm not going to speak about birds, but you've seen one of them on the cover page. But in technology, we know that the first manifestations were related to high aspect ratio wings, that is, in aviation. And of course, when we are, as we are in Toulouse, I think it would not be out of place to remind that Toulouse can be called a cradle of aviation, one of the cradles of aviation. And also, I think we can also say that here started one of the developments of ground effect phenomena. And let me remind you that in 1817, a person called Clément Ader had written a letter to a general who was in charge of the, if I remember well, 12th Division of Cavalry here in Toulouse. And in this letter, he wrote, "Mon général, je voudrais attirer votre attention à la découverte que je donne gratuitement à mon pays. Et c'est navire aérien, navire aérien." And in English it sounds as, "My general, I'd like to draw your attention to a discovery that I made and that I give for free to my country." And he spoke about a ship in air, airship or wing ship. so he already spoke about something we are discussing during this symposium. He went still much further. In 1890, he built 3 cutters, and these cutters used the first one was called EAGES, and it had sufficiently large aspect ratio, and also used some kind of power augmentation in its initial form. Then, of course, we have to remember that Wright brothers reported that their gliders flew much larger distances when a feet or so near the ground, near the sand, where they were experimenting. Around 1910, the pilots reported some queer and unusual feeling, which was then characterized and coined as cushioning effect, and which now allows to large Airbus planes to land so softly, as was remarked by Mr. Fisher during our excursion. In early 30s, the public perception went farther than just thinking that ground effect is a kind of aerodynamic nuisance, because of the experience of Dornier DOX seaplane, when the payload was increased and the range was increased during transatlantic service in the early 30s. In the late 60s, Boeing worked on a project of an anti-submarine airplane, which we may now call ground effect machine, which was called Lowboy. Lowboy had very high aspect ratio of about 12, which exceeds aspect ratio of today's airplanes, which have something like 8, from 8 to 10 maybe. And the span was about 52 meters, so it was quite a large airplane or ground effect machine. This was the project of Boeing in the 60s. Then there were several other projects concerning large aspect ratio wings, and this is an interesting project which was developed by a Swiss engineer, Mr. Weiland, in his contract work with the American company US West Coast. And this was a huge machine conceived, arranged in a tandem, but as compared to Mr. Yor's tandem, it had 2 wings of very large aspect ratio, and the span of these wings was to be about 152 meters, whereas the length of this machine was about 213 or 220 meters. Now I'll tell a few words about the theoretical research. Of course, we should start with Prandtl, and we should give credit to his intuition. He intuitively applied the method of matched asymptotic expansions, treating the large aspect ratio wing as a lifting line in the far field and as a 2-dimensional cross-section of a wing, say flat plates at an angle of attack, in the near field, and then he matched. He matched by taking account of the downwash and using the Kutta-Zhukovsky condition at the trailing edge to relate the far field and the near field. And this gave him an opportunity to reduce the problem to a relatively simple, in those times, integro-differential equation, which was then solved by different methods. Then this idea, of course, was exploited quite often, and it's still quite useful, because now with CFD we have a problem of pattern recognition. The data flow is so large that we have to do what is now called data mining to understand where we are. There are so many numbers coming out of computers that there is again need, in my understanding, in simple models like Prandtl's lifting line, in order to see where we are going with computational fluid dynamics. Now this was extended to many kinds of flows around large aspect ratio wings. In oblique flow, curved and yacht lifting line was done by Dorrit Nielsen in 1944. Then supercavitating, planing, in the case of planing of a lifting line on the surface of fluid, we have the so-called green paradox, because we have to treat also the free surface, which drops off logarithmically in two-dimensional flow. So we have to produce matching, because logarithmic behavior of the free surface is related to point source two-dimensional behavior. And of course, in 3D, we have much quicker decay of perturbations. So matching 3D to 2D, we can get rid of this logarithmic behavior of the free surface and obtain a final unique solution. There was also a work for a lifting line with a jet flap, unsteady lifting line, and some work on lifting line in ground effect. Now I'll remind you again that Prandtl's lifting line concept in ground effect would imply that characteristic chord of the wing is much smaller than both the span and the ground clearance. And in relative terms, it would look like that, where L is the relative span, and HL, H sub L, is relative ground clearance based on span. So we now say that the chord is much smaller than the span and smaller than the ground clearance. The latter two lengths are of the same order, which reflects in a proper way the situation with airplane cushioning effect. So you have a very large aspect ratio wing which approaches the ground when the airplane is landing, or which is near the ground when the airplane is taking off. Now, what we do here in order to avoid direct solution of Prandtl integro-differential equation is first I write down the flow potential of a lifting line, which is described by equation. Is there any pointer? No, there is no pointer. There is a pointer, sorry. So this is velocity potential, perturbation velocity potential induced by a lifting line where gamma is a loading or circulation of, which we do not know and which certainly changes span-wise. In order to avoid, because we then would have to go for smaller clearances, and you'll see some difficulties that might occur here. Sometimes it is quite convenient to use another formulation for phi, which can be derived from 6 by integration by parts. Now, adding two scalar quantities, this potential of the lifting line, a potential of the mirror image of the lifting line, which is equivalent to taking account of the solid wall. We have a sum of two potentials and asymptotics near the lifting line. That is, behavior of this potential in close proximity to the lifting line, which is necessary for matching, is this formula. It's given by this formula. But it's important that the first term simply says an interesting thing, whereas lifting line is a 3D object. When we come closer to the lifting line, at distances of the order of chord, we come to a 2D, and we see here a two-dimensional point vortex potential. This is a well-known phenomena. If we look upon Earth from far, this is a sphere, and this is a ball, so to say. When we come closer, this is a plane. Here in mathematics, you can also show that if you have a finite line but come very close to one of the points, should be far enough from the ends, you have 2D instead of 3D. We can also easily calculate what Prandtl would call, and we would call now a downwash, induced downwash, which is due to the wing itself and its image. And we know from what has been said and discussed here and in the papers, both classical and new, that the downwash is reduced due to the ground effect. This is because the mirror image vortices rotate counterwise with respect to the vortices of the main wing. So we can write down the downwash immediately having this expansion, because this is proportional to the y term in inner asymptotic expansion of the potential near the lifting line. It is convenient to deduce an alternative form of the second term by integration by parts, and we see that the kernel of this integral, which should be considered as valeur principale, principal value integral, because we have this singular term, looks like that. The kernel is like that. And we can see also here by parsing an interesting thing, that if h goes to 0, then this term, as you can see, becomes 1 divided by z minus zeta. That is exactly the same as the first one. So the kernel becomes 0, which also is a sign of instability, which you may expect when calculating very close to the ground. Now, sorry, I probably... I should take a near field. When I come closer to the weighing of large aspect ratio, I just see two-dimensional section, depending on where, in terms of span, z, I am. So we can have, which is allowed by Prandtl's lifting line concept, have different sections and different profiles of the wing in sections. We can also consider the inner field, or the near field, as nonlinear. We can also use computational fluid dynamics results for 2D, steady and unsteady, and then match to the lifting line outside. So that what we see, which is also quite natural, we can construct the potential of the flow past wing section, and then when we go far, if this section is lifting, then the first term would certainly be a point vortex potential. So we see even in words that there are now two 2D point vortex potential in what I might call an overlapping region. So we see that the outer field and the inner field can be matched together. We can then use results of this matching to construct the uniformly valid flow picture and to obtain in mathematical terms a unique solution. So when it is done, we can easily calculate sectional lift coefficient. We can also calculate by integration the overall lift coefficient. We can, by multiplying, in the case of a flat plate, by multiplying the sectional lift coefficient by a sectional downwash, and then integrating, we can get induced drag coefficient, and this is all done in closed form. These are simple formulas which can be calculated, and now we see that we can calculate what is called inverse efficiency, mu, which is the ratio of the aspect ratio to the effective aspect ratio. And we now know after these discussions that effective aspect ratio is not the same as a geometrical aspect ratio. In the case of ground effect, of course, we all know now that the effective aspect ratio is not only depending on the aspect ratio in geometry, but also on the distance to the ground. So we see that it also depends, not only depends on the aspect ratio lambda, but also on HL. So for the same lambda, we can go closer and get larger lift coefficient. This line represents a calculation with use of the simple formula obtained by meshed asymptotic expansions. This is the data which was collected by Mr. Ando from Japan, and this collects data from different sources published. And this is something interesting which I'll show in connection with the limiting process applied to these results. So we certainly see then when the wing comes closer to the ground, then the effective aspect ratio becomes larger. So it goes to 0, theoretically goes to 0. It means that the downwash is almost completely annihilated. And we see that the correspondence, even with the use of this simple formula, is relatively good. Now we can construct in the same manner mathematics for two lifting lines, a tandem of high aspect ratio wings, in principle of different aspect ratio, which can fly as a composition, which can fly with different relative distances to the ground. So all this mathematics is relatively simple, and the algorithm is the same. We have two lifting lines near ground effect. Now we sum four potential, the first lifting line, second lifting line, and their images. It is interesting that no matter what are the boundaries, in this case we have only one wall, we can have another wall, that is we can consider a lifting line, a large aspect ratio wing, and a channel, no matter what are the boundaries. It may be three boundaries. In the inner field that is near the lifting line, you always have 2D result. This is because the chord is much smaller than the distance. So when we come closer to the chord, then the ground goes to infinity. And this is quite useful because we can always employ the results, 2D results from classics or from computational fluid dynamics, if necessary. If it is reasonable to complicate this simple approach. Now, for a tandem, the result that can be obtained numerically, if I take a lift coefficient of a tandem in ground effect and then divide by lift coefficient of the tandem in unbounded fluid and do the same for single wing, it appears the tandem has slightly larger relative influence of ground effect. There is some explanation to that. Now, let's try to obtain another limiting case, which can be called now extreme ground effect, but span-based extreme ground effect. Now, we assume that the distance from the ground related to the span goes to 0. So we have a large aspect ratio wing very close to the ground. The airplane approaches the ground. If you remember yesterday's excursion, Airbus excursion, I think the relative distance was about 5% for an airplane standing on the ground already. So it is really quite considerably extreme ground effect. Now the process leads to a non-trivial limiting flow, which is a result of coming together of lifting lines and corresponding mirror images. So there is a lifting line, if I take a single lifting, which approaches the ground. And there is the mirror image, which approaches the ground from the other side. So there are two lifting lines which come together, and the gap becomes infinitely small. So what comes out of it? If we consider a source and a sink, this is a classical result, and these two singularities tend to approach each other, there is a simple question. What would come out of it? Would the source eat the water generated by a sink, and we would get 0 at the end? Not necessarily. We can obtain a dipole if we assume that the distance multiplied by productivity of a source or a sink is constant. This is what we call moment of a dipole. So this is almost the same case, but with lifting line. So we can call this process quadrupolization or quadruplication. Now, this is governed by simple ordinary linear differential equations, both for a single wing and the tandem of large aspect ratio and extreme ground effect. So how it is done? If I take the results of the previous part and write it down in form of Prandtl's integro-differential equation, you see why it is integro-differential equations. We are looking to solve for gamma, and we have gamma here, and we have derivatives of gamma with respect to the span-wise coordinate under the sign of the integral. So it is integro-differential equation. Now again, I draw your attention to the kernel, which goes to 0 when h goes to 0. So we can now use constructively this interesting singularity of extreme ground effect for a lifting line. We can single out, you see, we cannot expand the kernel in terms of HL directly, because we have non-uniform continuity of a function here. And we would get divergent integrals. So we have to process this quite delicately, and I have to split this integral into 3 parts. These are outer parts, and their contribution is of higher order, and this is what I call inner part. Inner part takes account of the fact that z minus zeta is not necessarily larger than h when h goes to 0, because we can have situation when z comes very close to zeta. So in this situation, zeta minus zeta squared, sorry, the bracket should be here, is of the same order as h squared. So, and this is the most important contribution. Now, I take this, after evaluation of these integrals, I take the inner integral, and of course the process should be organized in the following way. Eta is a fictitious small parameter which should be larger than h in order to be able to perform expansion in the outer integrals. And now, within this, with the stretch of this relatively small distance of the order of h, we introduce stretching of coordinates, which can be interpreted as Prandtl's or mathematical boundary layer. And then we work on a kernel by expanding gamma. It can be done outside of the edges of the tips of the wing, expanding gamma in Taylor series. And then we have a very simple integral, which gives us just second derivative of gamma with respect to z. So what we have finally, we have had Prandtl's integro-differential equation. We went to 0 with h, and now we have Prandtl's equation, but in the case of extreme ground effect. So this has been integro-differential, and this is ordinary differential of the second order, which can be resolved very quickly, of course. Now, alpha is the angle of incidence of a wing section, which depends on span-wise coordinate. HL is constant, is well, relatively small. And then gamma L is the distribution of circulation of, which is proportional to loading of the wing. And loading, of course, goes to 0 at the tips. So now we can integrate for some basic span-wise distributions of the chord. Rectangular wing, the formulas are quite simple and straightforward. If we consider a downwash now, downwash is now represented by a simple second derivative of gamma, of the loading. So we can easily see that the Betz optimal requirement, which was introduced by Betz, I think in 1922, is that constant for the optimal in the sense of minimal drag, induced drag for a given lead, distribution of downwash should be constant. So the downwash along the span of optimal large aspect ratio wing should be constant. So if we take it as constant, we easily see with gamma 0 at the tips that it becomes a parabolic distribution of loading rather than elliptic. So we see now an obvious peculiarity of extreme ground effect or ground effect, that optimal distribution of loading is no longer elliptic as predicted by our classics, but it is parabolic. It is parabolic. So we can see from the structure of the previous differential equation that we can have very easy solutions for this optimal case if we suppose, for example, that the plane form is parabolic or the twisting is parabolic. So in this case, I take plane form parabolic is parabolic, and I easily get gamma 0, and gamma distribution is, of course, also parabolic. This is lift coefficient, which is very simple. This is alpha, the incidence. So I took here untwisted flat plate. Alpha is the incident of the wing section. HL, relative ground clearance based on span. This is relative span, and this is the downwash, which is also constant. And of course, we can also easily calculate induced drag and reduce all this to a Prandtl's form. You remember that the polar form, which was introduced supposedly by Prandtl, has this form. This is the coefficient of induced drag. This is the coefficient of lift. And this is a coefficient which shows what has become the aspect ratio in efficiency terms. You see this inverse coefficient nu, which shows how large becomes the aspect ratio near the ground. So usually in Prandtl's form, the drag coefficient is proportional to the square of the lift coefficient. And we certainly easily calculate the ratio of the effective aspect ratio to geometric aspect ratio, and it becomes 4 divided by 9 pi HL. Very simple. So if we get back to previous result we showed for moderate ground effect, and you saw there was a tangent for h tending to 0. That tangent is exactly represented by this very simple formula. So now a tandem of lifting lines in extreme ground effects is no more complicated. Now the same limiting process leads us to two simple ordinary differential equations of the second order, and this describes loading of the first wing. This describes loading of the second wing. Of course, this is an extreme result, which shows that the first wing, when h goes to 0, almost does not experience influence of the rear wing, whereas the rear wing certainly has influence of the forewing in its right-hand side. And these equations are easily solved for plan forms as we want. But again, we can easily see that because there are second derivatives here, we can easily obtain optimal tandem configuration loading distributions, which should be parabolic. So if I assume that both distributions, gamma 1, first wing, gamma 2, second wing, are parabolic, you differentiate z squared, and you have a constant, so you can just determine the constants. And you obtain, finally, very simple results, both for rectangular plane forms and, as I said, for optimal parabolic loading. And this is the first lift coefficient of the first wing, lift coefficient of the second wing, lift coefficient of the whole tandem. Sorry. Yes, sorry. This is the sketch showing what's the gain obtained from optimal lifting distribution of loading. This is rectangular wing, which is worse than parabolic wing. Parabolic distribution is the best. And this limiting case, and I think this is probably all about the model. Also, I wanted to show that when we determine induced drag coefficient for a tandem, the formula, the structure of the formula is exactly the same as for the tandem out of ground effect, classical formula obtained by Betz. But this is a limiting case. Now, I want to tell a few words if I have time. Do I have a minute? About what can be called span-dominated and chord-dominated ground effect. So in the case of airplane, the wing is relatively large aspect ratio. We have ground effect mostly due to reduction of downwash, because no pressure is collected under the wing. The wing is too far from the ground, but still there is ground effect, and this is due to reduction of the downwash. And downwash is reduced because the downwash generated by the mirror image cancels the downwash generated by the main wing. So this is what can be called span-dominated ground effect. In span-dominated ground effect, as this results based on previous formula show, we have lift coefficient which goes up when the distance becomes smaller. So we still have lift which goes up for a constant angle of incidence. And we have drag coefficient which goes down because downward goes down. And lift to drag goes up, so we still have ground effect. Now, it is a common conception that in ground effect, the lift goes up and the drag goes down, which you see here. But let's pass to another limiting case, or to the case of a ram wing ground effect, or what can be called chord-dominated ground effect. When the distance is smaller than the chord, then we're able to collect pressure, or to stagnate pressure under the wing. And this is also ground effect, and lift-to-drag ratio grows when you go down, but the nature is a bit different. Because contrary to this, the drag coefficient can go up when you go down. So both lift coefficient and drag coefficient, this is chord-dominated, both lift coefficient and drag coefficient go up. These are limiting cases, and if we take a real wing of moderate or intermediate aspect ratio, we can find both. So we cannot state for sure that the drag always should go down. We can state for sure that if the lift coefficient is fixed, then the drag always goes down. But if the angle of incidence is fixed, then the drag can go both down and up, depending on whether we are closer to span-dominated, like in aviation, or to chord-dominated, like ram wing ground effect. This is what I wanted to tell you, so thank you very much for your attention.
So thank you, Kirill. There is some time for some questions for this very didactic presentation. Yes, Bernard?
For your last remarks about the lift and the induced drag coefficient.
Mm-hmm.
What is important is not the lift, it is the ratio lift over drag. So you should give your results showing the ratio.
Oh, yes,
Lift over
it's
drag.
correct. It's correct.
Yes.
We have to, in this case, to compare on the common basis these results, because in one case we have chord-related ground clearance, in other case we have span-related ground clearance. But if we compare, in principle, ram effects usually stronger than span-dominated ground effects. Lift-to-drag ratio goes up quicker when the distance diminishes.
And also, it could be, one can add that it's not necessarily useful here to compare the ratio because the viscous drag has not been taken into account, so...
Sure. Well, speaking about viscous effects, of course, as usually in the lifting line, engineering approach, so to say, we just add the friction drag or viscous drag, where you can use some kind of classical formula for turbulent boundary layer equivalent flat plate friction drag. Just add it, and then you can obtain, of course, easily the maximum lift-to-drag ratio for a given configuration of the wing, which certainly depends. It's proportional to the square root of the friction drag coefficient, but can be different depending on what is the effective aspect ratio. So these models give possibility of simple estimates when one understands fairly well what are geometric configurations and what are the craft configurations one considers.
I actually like to make a comment on one of your pages, maybe the one which gives the downwash
downwash, I think.
I don't know, maybe it's this one, or I'm not sure of it.
Yes.
No, it's after, I think.
Number 9, number 10.
When you make HL tending towards 0 and you gain alpha I, so it's later.
Yes, it should be later.
Okay.
So. You speak about the limiting process.
Yes, the limited process. So I don't know where it's 10 or 11. Maybe it's 11 in fact, because just after there was this curve.
Somewhere here.
11.
Okay.
Yes, that's it, in fact. This is very interesting, and maybe that the student will be surprised. You see that this quantity is depending upon HL to the power 2, and the limiting process depends only on HL. And effectively it's true, so when the limit is done correctly, we find that at the beginning we thought that something was depending upon HL to the power 2, and at the end it's only to HL. So it's
you mean to say that what is the scale of this boundary layer region? Well, of course, this is always a question: how should we stretch the coordinates? But the obvious principle is what is called the least degeneracy. The least degeneracy. So in the case when this is smaller than this may happen when z is far from zeta, or zeta is far from z. Then, of course, we can neglect this. And this is the degeneracy to the outer flow. But if we want to keep as much as we can in the inner limit, then we have to keep both terms here. And this prompts that this difference should be of the order of h.
That's right.
I don't know whether I understood your question.
Okay. Is there any question?
One can organize the same process. For example, if I write out a lifting surface equation, and then I add mirror image, and then I consider a limiting process when h goes to 0, either based on span or on chord, because this may be, say, a rectangular or moderate aspect ratio wave. Then one can show, when doing accurately this limiting process, that this is again a quadruplication. So what one gets out of lifting surface plus mirror image when h goes to 0 is, in linearized version, for example, this is a Poisson equation in 2D. So it's again, instead of integral equations, integral singular equations, we degenerate, so to say, if I may say so, to differential equation in partial derivatives with one dimension less. It's again the same channel flow phenomena. We have 3D when the wing is far from the ground, and we have 2D because everything is determined by the channel flow, where fluid moves in longitudinal and lateral directions and is restricted to move in vertical direction.
Okay. Thank you again.
Do I have a second? Okay.
No. There is some modification. At the beginning I said that there will be a coffee break. Unfortunately there is a small delay. So we are going to go on immediately with the film of Professor Fischer. And maybe that the coffee break will be later. We will try to do it.
May I have 1 second, just 1 second. I want to tell to those who do not know that in June last year, we had in St. Petersburg international conference called EAGES2001, ground effect machines, including not only wing ground effect, but also air cushion vehicles. But there are the number of wing ground effect papers is much larger than that of air cushion vehicles. So there is a volume, and I'd like to present this volume of proceedings to the school, to the library of the school. And someone who is interested may write, and we can prompt you how you can order proceedings from St. Petersburg.
Thank you.
The ground effect is reduced, that's for sure, and so you have less vortices, let's say, at the tips. So what's the optimum way of finishing the wings? Because you know in regular aircrafts you have winglets and so forth, but here you really don't need them. So I mean, how do you try and finish off the wingtips?
Now here of course, an efficient way, which you can see, which you have seen in all crafts, real crafts which were demonstrated, is fitting end plates. Because for a given span, the end plate gives more effective aspect ratio. So I would say that as the span increases, you need less the end plate. For large aspect ratio wings, the relative influence of the end plates is very small. So you can get rid of the end plates. But when you reduce your span, then you reduce your efficiency unless you put the end plates or do something else. For example, provide some lateral curvature to the wing. As far as winglets are concerned, I think that all devices that fight with parasite vortices, useful in aviation, are useful here. Maybe to less extent because of this cancelling phenomena related to ground effect. But I think that one should try different methods of reducing induced drag, which is the major component of the drag in this case. I don't know whether I understood your question well.